of the world now look into space, to the moon, and to the planets beyond. And we have vowed that we shall not see it governed by a hostile flag of conquest, but by a banner of freedom and peace. We have vowed that we shall not see space filled with weapons of mass destruction, but with instruments of knowledge and understanding. For space science, like nuclear science and all technology, has no conscience of its own. Whether it will become a force for good or ill depends on man. But I do say that space can be explored and mastered without feeding the fires of war, without repeating the mistakes that man has made in extending his writ around this globe of ours. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
It's one small step for man, one giant leap for mankind.
When it comes to understanding the universe, we are only beginning. Humankind continually searches for patterns, trying to figure out, what is the universe made of? How does it work? How does our planet, our solar system, our galaxy fit in with the other pieces? And what don't we know yet? Helping us discover more pieces of the puzzle will be a new instrument on board the International Space Station, called the Alpha Magnetic Spectrometer, or AMS. AMS is not a telescope. Rather than looking at space, it will sift through space, studying the high-energy particles of cosmic rays. From the unique vantage point of Earth orbit, the AMS experiment has the potential to answer questions about the origins of our universe. The study of high-energy particles might help in the search for dark matter and antimatter in the universe. Nobel Prize-winning scientist Professor Samuel Ting, well known for groundbreaking particle physics work on Earth, has collaborated with an international team to create the Alpha Magnetic Spectrometer, a high-energy particle detector that takes particle science into space. With over 300,000 data channels for detection and over 600 onboard microprocessors to analyze the data, the AMS is sponsored by the Department of Energy, and scientists from 16 countries lent their expertise to create it. Parts from around the world were sent to CERN, the European Organization for Nuclear Research, in Geneva, Switzerland. NASA had the job to figure out how to get the 15,000-pound experiment into Earth orbit and have it operate in the hostile environment of space. The AMS was finally sent to the Kennedy Space Center, where it was ready to fly on board a space shuttle, the final large component of the space station to be sent on one of the last shuttle flights. Part of the shuttle crew is European Space Agency astronaut Roberto Vittori, who will operate the shuttle arm to grasp the AMS from the shuttle payload bay.
That means that I will have the responsibility with the shuttle robotic arm to take it from the payload bay and offer to the station. But behind that specific operational task, there is a very long history. I started about 25 years ago to study physics, to think about space, to think about the universe. And the specific of the search of the antimatter was one of my main and deep interests. It may appear as a very strange coincidence that today I will be the one to take this unique piece of hardware, take it from the bay of the shuttle and give it to install on the station.
For the AMS There are many benefits to having a fully functional space station as your home.
So AMS weighs 15,300 pounds. Most of that is science experiments. We do not have to carry our own power. We do not have to carry our own data systems to transmit that data back to Earth, because all of those systems are provided to us by the space station. It's a perfect example of how you can utilize the capabilities of the International Space Station to fly groundbreaking science experiments.
So how exactly does the AMS work? One thing it is not is a telescope. Telescopes measure photons, packages of light, both visible and invisible to the naked eye. This type of astronomy has given us most of our knowledge of the universe thus far. But the cosmos speaks to us in languages other than light. For the AMS, this will be the first time scientists study charged particles. Exploding stars and other celestial phenomena are thought to produce cosmic rays which travel across the universe and can wash up on the shores of our planet. The rays are composed of charged particles, but many of these are absorbed in our atmosphere, making it impossible to study them on Earth. But outside our atmosphere, on the space station, the AMS will be able to sift through these particles, helping us search for antimatter, dark matter, and the stuff of which the universe is made. A particle will pass into the AMS. Layer upon layer of detectors tells us the mass, energy, and velocity of the particle. Other detectors tell us which direction or path the particle took as it passed through the AMS. At the heart of the unit is a magnet that will make the particle curve one way or another, telling us whether it is matter or antimatter. And just how quickly does all this particle detection happen?
Faster than I can snap my fingers. Nanoseconds. In nanoseconds. AMS gathers data at a ridiculously large rate. We will see about 25,000 hits per second of cosmic rays coming into the aperture of AMS.
8, 7, 6, 4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge, expanding our lives in space.
Houston, Endeavour, roll program.
Roger, roll, Endeavour.
Houston is now controlling. Endeavour beginning to pull over onto its back. The roll program underway as Endeavour begins a heads-down position on course for a 51.6 degree, 136 by 36 statute mile orbit. Three engines now throttling down as Endeavour passes through the area of maximum dynamic pressure on the vehicle in the lower atmosphere. Approaching 1 minute into the flight.
Endeavour, go at throttle up.
Roger, go at throttle up.
Endeavour's three main engines now back at full throttle, all three engines in good shape. Endeavour's already traveling 1,300 miles per hour at an altitude of 11 miles downrange from the Kennedy Space Center, now 12 miles. At liftoff, Endeavour fully fueled, weighed 4.5 million pounds. It's already lost half that weight in propellant now, burned that weight. The next event is burnout and separation of the twin solid rocket boosters. That upcoming here shortly at the 2-minute 3-second point. Those boosters are burning 11,000 pounds of fuel per second. And standing by for separation of the solid rocket boosters.
Now you can see Venus.
Do the astronauts go there?
Not yet. Maybe someday. In fact, there are some really smart scientists who are working on something called antimatter to power spaceships into deep space. And all the fuel that they'll need, well, it'll fit in something about like this.
Cool. Where do they do that?
Washington State University.
Go Cougs.
Washington State University, because the world needs big ideas.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines, and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source, and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
Researchers have found a band of antiprotons ringing around the Earth, adding one more to the list of particles Earth holds within its magnetic field. Cosmic rays constantly rain in from space, colliding with Earth's atmosphere and creating a spray of new particles. Scientists have observed antiparticles before, but this is the first time antiprotons have been observed. Many of these particles become trapped inside Earth's Van Allen radiation belts, the donut-shaped zones around Earth where particles swirl around the magnetic field. The find, described in astrophysical journal letters, confirms theories that predicted the particle. The University of Rome detected these particles using Pamela, a cosmic ray detector attached to a Russian satellite. The satellite orbited through the South Atlantic anomaly, allowing the study of geomagnetically trapped particles in the inner radiation belt. Between July 2006 and December 2008, Pamela detected 28 antiprotons trapped in the spiraling orbits around the magnetic field sprouting from the Earth's south pole. According to researchers at Italy's University of Bari, the band is the most abundant source of antiprotons near the Earth. The find could one day open the door to fueling spacecrafts with the exotic particle, an idea already being explored by NASA's Institute for Advanced Concepts.
A lot of people are doing nothing more than getting huge quantities of mass and see if they can get a gravity wave to cause things to move. Well, that isn't what we're talking about at all. So I wondered if gravity could be related to its cousin magnetism. And so I found that when I take two magnets together, I have some neodymiums around here that I'm actually afraid of.
They're so strong.
They can danger you. But anyhow, you take a magnet, you go to put them together and they go clunk, right? But you take one of them, move it around, and all of a sudden it doesn't want to go together.
The repulsive.
So I got I ordered one at $5,000 a piece, with a 1/4-inch hole through between both of them, and I put a brass bolt and I tightened them down, forcing them together. And then I put them together in a thing that looks kind of like a rock. Okay, and then I got another one that didn't have magnets in it. And Galileo, in all his endeavors, he went up to the Leaning Tower of Pisa
and dropped
he dropped a big rock and a small rock. And his buddy down at the bottom kept telling him that the large rock and the small rock arrived at the same time.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Superb.
I got 9 guys that were not educated and didn't have pre-opinions on anything, and I dropped my 2 rocks. And I said, what I would like you to do is, I told them what I would like you to do is I would like you to take whichever one arrives first, get it in your hand, and when I come down the elevator, hand it to me. Now, they looked identical, except for...
and nobody knew what was inside?
Not, absolutely not. All the 9 times that I tested it, it's as though the one with the opposing magnet field extending out 3 feet on each side, I actually measured how
big the field is.
How big the field was. And on each side of one rock, I had a total of 6 feet. At any rate, the other rock arrived first.
Which one arrived first?
The one that had no magnetic field in it.
So you were able to cancel out gravity to a certain degree. You were able to cancel,
precisely,
reduce the mass gravity effect.
Precisely.
By opposing fields.
Isn't that nice? You bet. And got 9 signatures and I always skip. You
did that at Lockheed. What year was this?
Oh, at least 8 years ago.
This is the actual document of Boyd's where he proved that by altering the field in a falling body, the magnetic field, it reduced its mass gravity equivalent and canceled out the effects of gravity to a certain percentage. And he did a building 500 drop test conducted from a height of 59 feet. The location is in White Settlement, Texas, and the time was 12:20 p.m. and this was in 1995, December 12th. Nobody knows this.
I know it.
So gravity, mass gravity is not, you can alter it.
Well, gravity within itself has to have, gravity goes through anything that is solid and anything like iron or anything else. but it has to have a magnetic component, which may be canceling out within itself. But as soon as it got around my rock, it all of a sudden recognized the presence of my rock.
One of Einstein's students tried to merge electromagnetism and gravity, and he rejected it. But he didn't have an experiment like you did.
No, I understand. I know that.
Yeah.
But see, nature never uses English. It doesn't speak. It doesn't speak any language. But yet it's talking to us all the time.
Right.
And the key thing is to identify what it's saying.
David Madeira with Hemp Technologies. This is our first house in the United States. It's permitted. What you've just seen is the mixture. The mixture is the most important thing. That must remain consistent. As you can see from this wall, we do it in sections. Now these sections have to fit together, and that consistency of the mix is crucial. Now we did these on last week. We can take down the forms now and move them up. This is a big window here. We'll lay the bottom plate in it, and then this will be protected. So what we're using here is recycled plastic in reusable plastic shutter forms that lock together tight. Sometimes we have to screw them directly into the framing, but pretty much they'll unlock, and then we use them on the outside. For this bottom layer, we need to leave that shuttering on for 24 hours. And after 24 hours, we can remove that first layer of shuttering system. And then we take the bottom shutters and we move them up on top. Now, in the perfect world, we'd have enough shutters to do both sides. But right now we have to keep reusing them to go around the house. So with these forms, with regular concrete, you have a slumping that causes the bottom form to go out. With hempcrete, you do not have any of this slumping, so you don't have to worry about taking the form off too early. And with concrete, what would happen is pushing the form out. And that's why your forms have to be a lot stronger. And in this case, because we don't have any slump, we don't have to worry about that. Okay, so what we have here is the hemp shiv, or also called the hurd, which is the internal part of the stem of the plant. And that's mixed with a lime-based binder. And so with that lime-based binder and the hemp, we've got a negative carbon footprint. Now the difference between lime and concrete is that lime you don't have to heat up as much. Concrete you have to heat up to almost 3,000 degrees, which takes a lot of energy and does very poorly on the carbon footprint, whereas lime does much, much better. Now this binder, using the lime and the hempcrete together, you have a breathable wall, but yet air doesn't pass through, so you have a much more thermodynamic situation. Major differences between this and straw bale is when straw bale gets wet, it doesn't do as well as this. When this gets wet, it just dries itself out naturally because of its breathing capability. And so you never have mold, you never have dry rot, and you never have termites. And so this whole wall is going to breathe. So the cellulose properties of hemp are so much better than straw. Now, there might be some plant out there that's even better, but we don't know about it. Basically, what this does is, because of the lime-based binder, not only does it have a carbon negative footprint, it will pull carbon dioxide out of the air after the house is built, because the lime is trying to go back to being a rock, and it needs carbon dioxide to do that. That means this wall is going to get harder and harder and harder. Over time, it's going to petrify. So these walls will last for thousands of years, not 40 years like what we're used to building. See how well in winter conditions the hempcrete has held up. We've had freezing down to 8 degrees Fahrenheit here, back up to 32, back down. It's gotten to 40 degrees, and it's done extremely well in this weather. So once it warms up, we'll put the finishing render on it.
Cannabis hemp is the #1 food, fuel, fiber, paper, medicine out of any plant on Earth.
Amongst the thousands of products made from hemp, one of the most extraordinary is Henry Ford's plastic car. Built in 1941, it contained cellulose fibers derived from hemp, sisal, and wheat straw. The plastic was lighter than steel, yet could withstand 10 times the impact without denting.
Now, today we're able to produce over 50,000 different things from that plant. Practically everything you're looking at right now can be made from hemp. Now, 1 acre is only about 65 square meters. Not a very big area. But 1 acre of hemp will produce 500 gallons of ethanol. Well, that'll run your car a long ways. But there's new enzyme processes out right now that they tell me that they can get as much as 1,800 gallons of ethanol per acre. Now, 1,800 gallons would heat your house, heat your hot water, run your car, and you'd have a few hundred gallons left over. And don't think for a second that your car can't run on alcohol, because right now, over half the cars in Brazil are running on alcohol made from sugarcane. And hemp is a superior plant to sugarcane because it has the highest cellulose content. It'll produce the most alcohol by weight.
At Poet, we have a unique way that we process biomass into ethanol or cellulose into ethanol. We do that by first collecting the stover, which in this case is corn cobs and some of the light husks and leaves that come off the corn stalk. We then process that at our facility, basically take it through a milling process first. It then goes on to a pre-treatment step where we break down those particles even further through a enzymatic hydrolysis step where we convert the cellulose and hemicellulose into sugars. Those sugars then move to a fermentation stage where over time they're converted to ethanol. That ethanol is then separated from that mixture, and the remainder, which becomes a byproduct, then can be used to power not just the cellulosic plant that we're operating to do this whole process, but also can be used to power other facilities that could be located next door, such as a grain-based ethanol plant or an electric generating plant.
The American government government and the Canadian government had this plant listed as a non-medicinal plant. Now, if you look it up, the American government since 2003 have had medical patents on that plant. Medical patents for a non-medicinal plant? Does that make any sense to you?
My name is Rick Simpson, and I'm here in the beautiful city of Rijeka to speak about the use of hemp medicine. What's truly happened here is years ago, big money has manipulated governments and all kinds of organizations into keeping this plant away from the public because it's so medicinal. And not only that, it's an energy source. It can feed the planet too on top of that because the hemp seeds are one of the most nutritious things you can eat. It's endless what we can do with this plant, and then we will not be at the mercy of these big energy companies. We can all supply our own energy needs. This is the greatest medicine on this planet for treating all types of diseases like cancer, multiple sclerosis, arthritis, chronic pain. I could sit here and go on for the next hour because in reality this medicine works on all medical conditions. It promotes full body healing, and it doesn't just go after like the condition you have. Like when you go to the medical system and you have say a big tumor, the medical system tries to treat the tumor. They're not treating the underlying condition that's allowing your body to create that tumor. But when you take this oil, it goes after the underlying condition, plus it goes after the tumor. And I mean, we've just seen miraculous results with the use of this medication. And where it's harmless, why shouldn't we all have access to it? There's no reason that this plant couldn't be used to heal the world. And this is the direction we have to go. We have to take back our freedom, and we have to try to get rid of a lot of this pollution that's ruining this planet. Our planet is poisoned. It's in a horrible situation, especially like with that big Gulf oil spill in the Gulf of Mexico. Then you've got Japan spewing radiation for, well, heaven knows how long. That'll go on. And on top of that, this dependency we have on all this fossil fuels, again, the fossil fuels are poisoning our planet.
The biggest design challenge of the solar arrays was probably just their size. Each solar array is 28 feet long, and so we have 3 of them. And so when the solar arrays are fully deployed, the Juno spacecraft is almost 60 feet in diameter across the solar arrays.
Getting those
big solar panels to work the way we expect them to work and produce the amount of power we need, that's been a bit of a challenge.
The solar arrays are pretty interesting. When we deploy them, they'll be generating about 12 kilowatts of power. As we get further and further from the sun, that amount of energy will drop off until we finally get to Jupiter, where we're only generating 400 watts. It's not even enough to run a hairdryer.
Generally, with space exploration, you're pushing the envelope of technology.
Solar panels have improved a bit, the instruments have improved a bit and can run on less power.
A professor at Princeton named Gerard O'Neill conceived of the idea of putting large colonies in space, large artificial places where people could live and work. And what we did was to gather together a group of university people to look at the problem of how you build the very first colony.
This is Taurus, the concept that has evolved from the work of these teams of scientists and engineers. They believe the huge space colony could be built before the year 2000.
The space colony has the ability to provide a facility in space where human beings can conduct fruitful industry. The amount of sunlight that is present in every square mile of space is enormous, and that provides enormous energy. One of the things that one can do is to build very large solar power stations which collect sunlight.
The Earth-like environment would even simulate our gravity as the wheel revolves once each minute.
The other materials like food and water are maintained locally within the colony. The initial supplies are brought up from Earth, and then eventually the colony becomes self-sustaining by utilizing the sunlight that's available all the time in space, by optimizing the temperatures, by not having storms or things like that that damage crops. And we increase the carbon dioxide levels a little bit so the plants grow a little faster. By playing all these tricks, we're able to generate this fairly efficient farm in our design.
From dairy farms to manufacturing, the concept of living and working in space is a possibility with existing technology. That new space home, located 250,000 miles from Earth, would even have a far-out address.
George Washington, Thomas Jefferson. These were the founding fathers of the United States of America. They were hemp farmers. George Washington is very well recorded that George Washington used to like to sit out on his veranda at night and smoke his hemp in his pipe. Now, these are the same people that authored these wonderful documents like the Declaration of Independence, the Constitution. So it appears that the hemp didn't affect their thinking abilities.
for centuries. They acquired their name after Ferdinand Magellan's expedition circumnavigated the globe in the 16th century, and his crew used these cloud-like objects as aids to navigation. During the Age of Discovery, sailors relied on celestial bodies to reckon their own locations. The two heavenly clouds that attracted the attention of Magellan and his crew have fascinated people ever since. Recently, thanks to observations in the southern hemisphere using the most advanced telescopes, research on the Magellanic Clouds has taken a giant leap forward. The Magellanic Clouds turn out to be astonishing records of the very birth of the universe.
They provide a unique opportunity for studying what happens close to us in the universe, and that actually tells us a lot of things about how the universe formed and how galaxies form.
Astronomers throughout the world are eager to shed light on the Magellanic Clouds, hoping to reveal secrets about the earliest days of the universe. This program follows these stars on a journey of amazement and discovery. What is the true character of the Magellanic Clouds? This has been a huge mystery since the Age of Discovery. By the 17th century, 100 years after Magellan's expedition circumnavigated the globe, Europe was producing numerous star charts of the southern hemisphere. The constellations were pictured as various creatures: a flying fish, a chameleon, a resplendent peacock, a big-billed toucan. The constellations all had exotic names. And then there was Nubecula Major, Latin for large cloud, meaning the large Magellanic Cloud. That was paired with Nubecula Minor, or small cloud, the small Magellanic Cloud. Since they moved together with the stars, they were clearly no earthly clouds. They were heavenly bodies. But exactly what they were remained a mystery. The first detailed research into the Magellanic Clouds began in the 1830s. To conduct research into stars of the southern hemisphere, England had established a royal observatory at the Cape of Good Hope in southernmost Africa. Astronomer John Herschel worked there for over 4 years. He pioneered the study of celestial objects in the southern hemisphere. In 1847, Herschel published his findings in a 450-page report. This is the catalog of objects Herschel found in the Magellanic Clouds. Some 1,000 items are listed. There are numerous records of nebulae and star clusters, similar to those visible within the Milky Way galaxy. Herschel clearly thought of the Magellanic Clouds as constituting a galaxy. At the time, most astronomers thought that all celestial bodies lay within the disk of our own Milky Way. Herschel thought that these rather indistinct and nebulous objects must be extragalactic celestial bodies. To prove that, however, one would have to calculate the distance to the Magellanic Clouds. Alas, Herschel did not possess the means to do that. Are the Magellanic Clouds inside the Milky Way or outside? An epoch-making discovery at Harvard University finally solved the riddle. The crucial evidence was supplied by photographic plates stored here. This is the world's largest archive of astronomical photographs.
As you can see, we have cabinet after cabinet, many plates, 525,000 plates in this collection. That's 25% of the world's total of astronomical photographs just in this collection. And what is remarkable about that is that it covers more than 100 years of time, from 1885 to 1989. And we began photographing the southern skies early in the 1880s, so that the Magellanic Clouds are covered from that early time.
These photographic glass plates recorded light from the stars over long periods of exposure. They enabled astronomers to capture not only what Herschel could see directly, but even far dimmer stars in the nebulae. Around the turn of the 20th century, the data etched on these glass plates were processed by a team of female analysts. The position and brightness of every single star were meticulously recorded. The analysts were actively seeking variable stars, a popular quarry at the time. Variable stars are stars whose brightness fluctuates. Of particular interest were those whose brightness fluctuated in regular periods.
This was one of the very old ones.
This type of star could help prove whether the Magellanic Clouds lay inside or outside the Milky Way.
With the,
Wow, it's a 240-minute exposure.
Here we have a glass plate of the small Magellanic Cloud, a long exposure which is taken. Some of the stars will be variable stars, but you get them at only one moment on this plate. So this is a negative plate, and we also can then make from one of these plates a positive plate. And this one can then be used as a master. When you put them on top of each other,
Superimposing an image of a given area on top of another taken at a different time reveals any change. If the star's brightness is constant, it should be a perfect match. What happens when the brightness changes? Since brightness is translated optically as size, any variability is immediately apparent. This comparative method, done plate by plate, is a way of detecting which stars are variable. One of Harvard's female star analysts was Henrietta Leavitt, an astronomer later recognized for her analyses of variable stars. This is one of the photographic plates of the Magellanic Clouds that Leavitt analyzed. Out of 100,000 stars recorded on a single plate, she endeavored to identify the variable ones. Harvard still has her handwritten logbook. She assigned numbers to each variable star, comparing readings at fixed intervals and determining the periodicity of its variations in brightness. To prevent any mistaken attributions among the countless stars in the sky, she drew detailed star charts. After 4 years of research, Leavitt published her study of 1,777 variable stars in the Magellanic Clouds. In the course of compiling these data, she made a vital discovery. She noticed that variable stars in the Magellanic Clouds with the same period had the same brightness, or luminosity. Compared with variable stars of the same periodicity within the Milky Way, the ones in the Magellanic Clouds appeared fainter. The fainter the star, the farther away it must be. In the late 1920s, after Leavitt had passed away, detailed analyses revealed that the Magellanic Clouds lie far outside the Milky Way. Precise observations determined that the Magellanic Clouds are 200,000 light-years away. That's twice the diameter of the entire Milky Way. The Magellanic Clouds were definitely other galaxies lying outside the Milky Way. A large telescope subsequently revealed a deep relationship between the Milky Way and the Magellanic Clouds. This is the 2.5-meter Hooker telescope at Mount Wilson. This telescope enabled measurement of the distances to many galaxies outside our own. It revealed features of the Magellanic Clouds that differentiated them definitively from other galaxies. This is the galactic distribution, as currently understood. The two Magellanic Clouds lie approximately 200,000 light-years away from our own Milky Way. The larger one is approximately 1/10 the size of our galaxy. The nearest spiral galaxy to our own Milky Way is the Andromeda Galaxy, some 2.3 million light-years away. That's 10 times farther away than the Magellanic Clouds. So the Magellanic Clouds are two small galaxies very near our own. Edwin Hubble, the leading astronomer of his day, described the Magellanic System thus. The cloud is an independent stellar system and a close neighbor, actually a satellite, of the galactic system. A satellite is a space object that is gravitationally attracted to another and orbits it, as the Moon does the Earth. Hubble thought that the Magellanic Clouds similarly orbit the Milky Way galaxy. This concept of a satellite galaxy eventually became the standard view among astronomers. A major discovery was made in the southern hemisphere, in Australia. The two Magellanic Clouds together make up a single gigantic space object. The discoverer was an Australian astronomer named Don Mathewson.
If this object I discovered was actually visible, everyone would be astounded. It's an enormous arc of gas stretching right across the sky. In fact, it's more outstanding than the Milky Way galaxy.
Mathewson's starting point was a research paper written by astronomers at Bell Laboratories in the United States. Their measurements of intergalactic radio waves revealed filaments of gas in the skies over the northern hemisphere.
It was a rainy Sunday afternoon, and it was quite late, and I was just turning the pages of an astrophysical journal. I plotted their filament of gas, this sausage of gas, and I thought, well, let's extend that sausage a little bit, let's blow it up a little bit. So I drew a line on this polar graph paper, and I thought, gee, it passes through the large and small Magellanic Cloud.
The line Mathewson extended into the southern hemisphere from the mystery gas mentioned in the article went right between the Magellanic Clouds. And Australia had a radio telescope well suited to confirming the presence or absence of gases. It was the Parkes Observatory. Mathewson couldn't contain his excitement. He telephoned the observatory right away. The very next morning, Mathewson jumped into his car and drove to the observatory. The director had told him that the telescope would be offline for maintenance that day, so Mathewson thought that at night there might be a chance for some brief observations. It took him 4 hours to drive to the Parkes Observatory. At the time, this giant 64-meter diameter parabolic antenna made Parkes the largest radio telescope in the southern hemisphere. When Mathewson arrived, he asked the maintenance workers if he might borrow some time on the telescope.
So all the memories come flooding back, because it was the most emotionally charged episode in my life, really, the discovery of the Magellanic Stream.
Past 10 p.m. It was only after the maintenance staff had left for a late supper that Mathewson was able to use the telescope.
had it all plotted out, what I thought would happen. But of course in science things never happen the way you want it to. Nature is a very, is a teaser. It teases you and then all of a sudden drops you flat on your face. But tonight was completely different. For the rest of the 3 or 4 hours that it took, every position that I looked at with the telescope came out to be the right velocity and the right intensity.
When the telescope was pointed along the extrapolated path of the gas stream first noticed in the northern hemisphere, further traces of gas were found along the way. The gas trail seemed to be headed for the Magellanic Clouds. That's how Matthewson was the first in the world to actually establish a link between the gas trail and the Magellanic Clouds. Subsequent detailed observations confirmed that their distributions were aligned. This intergalactic belt of gas was named the Magellanic Stream. The Magellanic Stream is an extension of the same nebulae spotted by Ferdinand Magellan. It's a huge belt of gas, stretched out as if to curve around the Milky Way galaxy. It's 1 million light years in length. That's 10 times the diameter of the Milky Way. Like the contrail of a jet plane, the Magellanic Stream is proof that the Magellanic Clouds have passed that way. The gas is distributed as if it were encircling the Milky Way. So astronomers believe that the Magellanic Clouds are spewing out gas as they orbit our galaxy. The Magellanic Clouds, galaxies with a gas trail longer than the diameter of our own galaxy. To people of the northern hemisphere, the night sky of the southern hemisphere presents a strange spectacle. There's the constellation Orion. But it's upside down. And the Milky Way looks huge. The exceptionally bright area is our galaxy's nucleus. In the southern hemisphere, the mysteries of the universe seem all the closer. This is Santiago, the capital of Chile. It's surrounded by 5,000-meter-high mountains. Still bearing traces of its Spanish colonial past, Santiago is today at the forefront of astronomical research. On the way to a greengrocer's in a new part of town.
Hola. Gracias.
The shopper is Valentin Ivanov, an astronomer who was born in Bulgaria. Recently, he has been analyzing observations of the Magellanic Clouds made with one of the world's most advanced telescopes. He is affiliated with the European Southern Observatory, known as ESO. ESO has established 3 observatories in Chile from which to survey the stars of the southern hemisphere. With his telescopic observations, Ivanov has been creating the most detailed picture yet of the Magellanic Clouds.
VISTA is one of the newest projects of ESO, and it aims at creating large uniform maps of the sky. These are called surveys. One of the most important surveys that this telescope is producing now is the survey of the Magellanic Clouds, these green squares over here.
To produce a complete map of the Magellanic Clouds, Ivanov spends a total of 1/3 of every year at a mountaintop observatory. He has already taken over 100 of these trips. His destination is about 1,000 kilometers north of Santiago. It's in an arid zone that sees less than 10 millimeters of precipitation annually. This is the European Southern Observatory's largest site. Seven telescopes are located on the mountaintop here, at an elevation of some 2,600 meters. This is the one Ivanov uses. It's a 4-meter aperture telescope called VISTA. Installation was completed toward the end of 2009. Its technology is cutting edge.
VISTA is a special purpose-built telescope. Unlike other ESO telescopes, VISTA is designed to cover extremely large field of view in a single pointing. The field of view of VISTA is about degree by degree and a half.
How does VISTA compare in this regard to the Hubble Space Telescope? VISTA's field of view is about 500 times greater than Hubble's. In a single pointing, VISTA can take in a region much broader than a full moon. Ivanov and his VISTA team are attempting an exhaustive survey of the entire region containing both the small and large Magellanic Clouds and the bridge linking them. It's sundown. VISTA can now be engaged. In the control room, Ivanov will conduct observations all night long. The display shows stars within the Magellanic Cloud system.
The Vista Magellanic Cloud Survey already completed a number of tiles, and the data are publicly available. This data contain a lot of interesting objects, like this giant H2 region called Tarantula.
The Tarantula Nebula is an expansive gas located within the Large Magellanic Cloud. It's 1,000 light-years across. Its name derives from the hairy, spidery appearance of its gases.
This image that we see here actually is built from 3 different images, each of them in the near infrared. The advantage of the near infrared and the advantage of the kind of data that Vista delivers to us is that we can actually see through the dust. If you look at this region, this area on the sky in the optical, you'll see almost no stars because the dust and the absorbs the optical light much more than the infrared light.
Vista captured this image of the Tarantula Nebula. Compare it to an optical image showing ordinary visible light. It's clear that the Vista image reveals the stars hidden beyond the gas and dust. The Large Magellanic Cloud is said to contain as many as 20 billion stars. Vista captures them in stunning detail. Innumerable stars, nebulae, star clusters, countless points of light beyond the reach of ordinary optical telescopes, rendered here vividly and distinctly. Vista is continuing to survey the Magellanic Clouds at a level of detail unmatched by any other telescope. The Hubble Space Telescope has shown us how different in shape as well the Magellanic Clouds are from our own Milky Way galaxy. This nebula, in a remote part of the Large Magellanic Cloud, shines with extraordinary luminosity. It's gigantic, more than 30 times the size of the Great Orion Nebula. And out of the dark gas and dust, it is birthing countless new stars. One region in the Large Magellanic Cloud is giving birth to more stars than any other region in the Milky Way. Here is just one portion. Newly born stars illuminate the surrounding gas. It looks like a cocoon. Here, an accretion of gas and dust is displayed in silhouette, lit from behind by young stars. The largest mass looks like a seahorse. It's a huge object, some 20 light-years in length. The Small Magellanic Cloud also boasts magnificent nebulae and star clusters. The explosive birth of 100,000 stars. The energy they put out is said to be 60 times that of the Great Orion Nebula. Or look at the outskirts of the Small Magellanic Cloud. Innumerable young stars, born all in a group. And this sparkling, multicolored, open cluster has been called the Jewels of Magellan. Even today, The Magellanic Clouds are far more prolific than the Milky Way in the production of new stars. The Magellanic Clouds had been thought to be orbiting the Milky Way. But recently, a great discovery was made in that regard. The discovery was made by Roland van der Merel. Van der Merel spent 4 years directing observations of the Milky Way by the Hubble Space Telescope. His goal was to determine the mass of our galaxy, and he found a way to use the Magellanic Clouds to do so.
We thought that if we could measure exactly how the clouds are moving in the sideways direction, we could learn more about the mass of the Milky Way and about the distribution of the mass in the Milky Way.
Van der Merel's group thus observed the Magellanic Clouds directly in order to ascertain the speed of that sideways motion relative to the Milky Way. As a reference point, they chose to use a quasar, celestial bodies that are very far away and so essentially motionless. By using a quasar located beyond the Magellanic Clouds, as seen from Earth, they could measure the cloud's relative motion. They pointed the Hubble Space Telescope in that direction. The anticipated motion of the Magellanic Clouds was minute. It is the equivalent of observing a 1 millimeter movement from 100 kilometers away. That was close to the limit of Hubble's powers of resolution.
And then if you try this with a telescope on Earth, you run into several realistic problems with telescopes on Earth. For example, telescopes are subject to gravity. As the telescope moves, the gravity on the telescope is different, and the instrument distorts a little bit. And you see this in your images.
The observations with Hubble continued for 4 years.
Now, we cannot actually measure the motions of stars in the Magellanic.
Van der Merel's group succeeded in obtaining data on 25 of the regions into which the Magellanic Clouds had been divided. After analyzing the results for a full year, they calculated that the Magellanic Clouds are moving at an incredible 378 kilometers per second, 1.36 million kilometers per hour. This was 300,000 kilometers per hour faster than anticipated.
Initially, we were just very happy we were getting any results out that said, hey, we can actually measure the motion of the Magellanic Clouds. So that was our initial excitement for quite a while. And it was clear we were doing it better than anyone else had done it before, but it wasn't immediately obvious what we were learning.
To extract meaning from these speed calculations, computer simulations were conducted of the relative motion of the Milky Way galaxy and the Magellanic Clouds. The simulations were carried out at Harvard University. The movements of the Magellanic Clouds were minutely calculated, using the latest data on the size and mass of the Milky Way. This is the result. Contrary to expectations, the Magellanic Clouds do not orbit the Milky Way. Assuming the Milky Way is not unnaturally massive, the Magellanic Clouds will eventually fly off into deep space.
I basically computed things like the escape speed, which refers to the speed that an object would need to have to escape the potential of the Milky Way at its distance, at its separation from the Milky Way. And for the basic model that I had initially started off with for the Milky Way, the LMC was sitting at the escape speed. So the orbit couldn't be anywhere close to what we thought before.
So it was very normal for people to think for years that the Magellanic Clouds had been going around the Milky Way many times. Cortina realized that that couldn't be at that speed. They were going too fast. They were basically flying away from the Milky Way too fast, which means that probably they were just coming into the Milky Way for the very first time. And this was a very revolutionary thought.
So the Magellanic Clouds are not satellite galaxies of the Milky Way after all. They are visitors from afar, merely enjoying a chance encounter with our own galaxy. In a few billion years, they are fated to disappear into the furthest reaches of space, never to return. The true nature of the Magellanic Clouds is gradually emerging, and astronomical observations indicate that the clouds hold a key to understanding what the universe looked like right after the Big Bang. Paul Crowther is one of the scientists fascinated by the Magellanic Clouds. For 15 years, he's been studying one of the cloud's features in particular. What's attracted his attention is the Tarantula Nebula. At its center, there's a place estimated to shine with the luminosity of 100 million of our suns. R136 is its scientific designation. It was thought to contain a mystery object. Crowther set out to find out what that was. He conducted his observations with what's called the VLT, or Very Large Telescope, located in Chile. He pointed the VLT and its 8.2-meter diameter mirrors straight at R136 in the middle of the Magellanic Clouds. This is the very center of R136. The detailed view provided by the VLT reveals that what looked like one bright clump at its center is comprised of many stars, the brightest of which has been designated R136A1. With a luminosity of 10 million suns, it is, so far as we now know, the brightest star in the universe. Crowther performed a spectral analysis of its light.
The spectrum is kind of like the fingerprint of an object. It tells us what it's made of, it tells us how hot the gas is in the star. And so this actually is an infrared spectrum taken with a very large telescope of R136A1, and it reveals the presence of, for example, this is a line of helium-2, ionized helium, and this means the star is incredibly hot.
Thanks to this analysis, Crowther was able to start profiling his mystery object. This is how Crowther envisions R136A1 in the center of the Tarantula Nebula. With surface temperatures reaching 55,000 degrees Celsius, it burns bright blue. When it was born, it had the mass of 300 of our suns. To date, nothing comparable has been found in the Milky Way. These first-generation stars of the early universe, born right after the Big Bang, were unlike most of the stars we see today. They were formed directly out of hydrogen and helium gases, and they were all blue giants. In the Magellanic Clouds, there are many such stars. The Hubble Space Telescope has captured a number of ancient galaxies that contain these blue giant stars. All these galaxies are more than 13 billion light years away. So what we see now is how they looked 13 billion years ago. In other words, just moments after the universe was born. Ancient galaxies, glowing bright blue. The sheer number of blue giant stars, similar to the one Crowther has been studying, is enough to impart a blue color to the galaxy as a whole. These galaxies, born just after the creation of the universe, are a mere tenth the size of the Milky Way and have irregular shapes. In size and shape, they resemble the Magellanic Clouds. That is why scientists believe that studying the Magellanic Clouds will provide insights into the evolution of our own galaxy.
Well, so the interesting thing here is that we've learned a lot about structure formation in the universe over the years. And in particular, what has been learned is that structure forms by smaller units coming together. So if you're a big galaxy like the Milky Way, you really started out as lots of little clumps that fell together over time.
One scenario for the growth of the galaxy would go as follows. In the earliest stage of the universe, there were only small, irregular galaxies like the Magellanic Clouds. These small galaxies collided and merged repeatedly. In this way, so the theory goes, over the course of billions of years, larger galaxies like our Milky Way were formed. Van der Merel believes that the Magellanic Clouds are in fact holdovers from the earliest days of the universe, small galaxies that only now are brushing past our own larger galaxy.
In the early universe, soon after the Big Bang, we believe this happened all the time. There were bits and pieces of galaxies falling together to form the first real galaxies that then later grew over time. Nowadays, in our current universe, this is actually a pretty rare occurrence. So the fact that we're seeing the Magellanic Clouds pass the Milky Way right now is very unusual at some level, but it really gives us a glimpse of what the universe was like more typically when it was much younger, when galaxies were falling onto each other and merging together all the time.
The Magellanic Clouds had been thought of as satellite galaxies. But it turns out that they are actually leftovers from the very beginnings of the universe. Small galaxies linked together, spewing a plume of gases behind them as they rush past us. At the Vista Telescope in Chile, observations of the Magellanic Clouds are ongoing. The detailed mapping of the Magellanic Clouds, based on the Vista surveys, is expected to be completed in 2017.
Vista is continuing the observations of the Magellanic Clouds, and we are extremely lucky to have this exciting and mysterious galaxy next to us, because it has been a wonderful playground for astronomers for more than a century now, a couple of centuries, and I'm sure it will help us to reveal many more secrets.
The origins of the universe, the birth of the galaxies. These are the mysteries to which the Magellanic Clouds hold the keys. As humanity peers into the southern night skies, that quest will continue.